Hello everyone, this is Mrs. Martin here with notes today on special systems of linear equations. Last time we met, or we talked about notes, we talked about solving systems of linear equations with substitution methods. So far, if you haven't seen them already, we've seen an introduction on systems where we graphed them, and that's why I've got my Desmos up here on the left. And then we learned how to solve them using substitution. Today we're going to talk about some special things that might happen as we're working through systems and just some things to be on the lookout for as we solve these systems of linear equations. If you haven't seen the previous two videos, I would stop here and watch the last two on the intro of linear systems of equations and then the solving systems of linear equations using substitution. I would watch those first, because this one might be a little confusing if you haven't seen and worked with the other two. So moving forward, we are currently working out of section 5.2 of our textbook. So in case you have your textbook at home and you're trying to follow along with that, we're working out of chapter 5 for systems. And this particular problem is problem number 12 on page 245. And so just to kind of recap, we're solving this system using substitution. We could graph, right? That's very easy for us to do. We have the capabilities to do so. I would put negative 5x plus 3y equals 51. And then underneath that, I would put our second equation, which is y equals 10x minus 8. And so from our work with systems so far, we know that we're looking for this point here, this point of intersection between the two lines, the red line and the blue line, which, lucky for me, Desmos color-coded with the equations I wrote on the right. So when I use the substitution method, my answer to this system should be the ordered pair 322. So I'm going to go ahead and set up my answer for these in parentheses right next to it. Okay, I'm just going to leave some blank spaces here because I know that my answer, here, let me scoot that over a bit. I know that my answer has to be an ordered pair. And even though I graphed it and I know the answer, I want to prove that using some algebra. So let me go ahead and scoot this up a bit. And let's go ahead and start our work with this. So luckily for us, let me change this color to yellow. Our y is already isolated in the blue equation. We've got y equals some value here. Okay, and since I've got y equals, we're already set up to substitute. In the last video, we saw what would happen if we didn't have a variable isolated. We'd have to do that first. But luckily for this problem, y is already alone. And so I can just plug in 10x minus 8 into the variable y of the red equation. So let's do that together. So I've got negative, and again, this is just review, nothing new from the last video. Negative 5x plus 3y equals 51. I'm just going to rewrite that for myself so I can really see what's happening with y. I see right there that I'm going to have to plug in. And I have negative 5x plus 3, and instead of writing y again, I am substituting the blue equation in for y. And I'm using parentheses so that I remember to multiply. Okay, so continuing on with this, we know in class that we should be distributing here. We're starting with our parentheses. Remember your order of operations, so I'll start there. Negative 5x plus 3 times 10. That's positive 30x, and positive 3 times a negative 8, that's negative 24. Okay, so continuing on from here, we would combine like terms. I've got 25x here, 30 minus 5, minus 24 equals 51. Let's go ahead and add 24 to both sides. And then I've got 25x equals 75. And when I divide both sides by 25, I end up with x equals 3. So am I right? Did I do my math correctly? And if I look over at my Desmos graph, the answer is yes. 3 is our x value of that ordered pair. So far, so good. We've got 3 in for part of our answer. Now, on a test, you wouldn't have the graph. You wouldn't have Desmos available on the test. But we do know that we need the y value now. Okay, and as we mentioned in the last video, there are ways to check to make sure we can plug in our solution. Just to confirm, I won't be doing that today just for the sake of time. But again, if you need to review that, please go back and feel free to watch the video again so that you understand what's going on. So now I've got my x equals 3, and I am ready to substitute that in somewhere else. So let's see here. 3 is going to go into an x value. Now I really have options here again. I could choose either the red function to work with again or the blue function to work with again. It doesn't really matter which one I choose, but I'm going to go ahead and stick with the blue one just because we haven't used it yet. And it would be nice to see a little bit of work with the blue one. It's also nice that y is already isolated, so all I need to do is plug into x and it's going to give me an answer. There's going to be very little properties of equality being used when solving the blue equation. So let's go ahead and write this out. Y equals, now I should end up with the 22, right? Because that's our solution over here on the left. 3, 22. That's our ordered pair. So I should end up with 22, assuming that I did everything correctly. So let me substitute my 3 in here. Y equals 30. That's 10 times 3. Minus 8. And 30 minus 8 is 22. We're happy. We knew that was a solution because we graphed it, but now we showed that it's a solution using algebra. Okay, so there's my answer, 322, the answer we were expecting, and the answer we've just shown using algebra. Okay, so that's a simple system of linear equations that we solved using substitution, and it's called substitution method because, of course, we are substituting one equation into the other, and then later a part of a solution to get the second part of our solution. But today's video is really focusing on what happens when we have a special system of equations. So let's look at another example together and see what happens when we have a special system of equations. So here's one type. Okay, let's start with, and this one's coming out of section 5.4 of your textbook. We are going to look at number 2. So number 2 on page 257. Says negative x plus y equals 1. Let me stay color coordinated here. I apologize. Negative x plus y equals 1. And the other equation in the system is x minus y equals 1. Okay, so there's 2 equations that make up a system. And as I mentioned before, we need to have an isolated variable, and we don't have one, which makes things a little difficult. It just means, but it's really just a matter of us isolating one of those. So let's work with the blue equation because I've got a positive x. So I'm going to move this over to the side just for a second. X minus y equals 1. I'm going to add y to both sides. And so x equals 1 plus y. Remember, we don't combine those. Those are not like terms. And now x is alone. So now I've got a variable isolated, and now I can proceed with my substitution method. Okay, so I know that when I get a solution, my solution should be an ordered pair, right? So let's go ahead and work with this. I'm going to start with yellow here. And I'm going to substitute 1 plus y this time into my x value. Now we have to be very careful here, okay? X equals this stuff over here. So it's very important that I plug in that stuff in for my x variable, not y like we did in the previous problem. Okay, so watch out for this negative sign. Okay, it's still there. And then I've got 1 plus y instead of x. We just substituted. and then the plus y next to that equals 1. And I know I'm doing a good job because I've only got y variables in here. Okay, that should be another helpful tool for you. If you have more than one variable, then it is possible that we substituted the equation into the wrong variable to begin with. So make sure you only have one variable. We only know how to solve for one variable at a time. And then I'm working through this. I've got negative times 1. Now, if you're a little hesitant about this negative sign, some of you like to put the 1 in the front. That's fine. So negative 1 times 1 is negative 1. Negative 1 times y is a negative y. And then I've got plus y equals 1. Now, something very interesting happens here. Can you see it? When I combine like terms, and I get negative y plus y, that's a 0. Okay, y minus y, that's 0. So something a little strange happened there. And then I end up with negative 1 equals 1. And you guys might be super confused right now because negative 1 is not the same as a positive 1. If I owe $1, it's not the same as having $1. So when this happens, we learned at the beginning of the semester, at the beginning of the school year actually, that when we have two things that are not the same on both sides and I have no variable, this has a very special answer. And that answer is no solution. You remember that? I hope you do. No solution. And if I've got no solution, there's really no more work I can do. There's nothing for me to plug into the other equation. It wouldn't matter if I tried the top red one and plugged it into the blue one instead. Any way we try it, we're going to have no solution. So there is no ordered pair. Now, how can we prove that with graphing? Let's look at it together. I'm going to type in negative x plus y equals 1. And before I type in the next one, what's this going to look like? Just thinking about it for a second. If I have something that's no solution, what do you think those two lines should look like? If you're thinking in your mind a very special word that we practiced in class called parallel, then you were absolutely right. If I have no solution, the two lines are parallel. The two lines are parallel, which means they have the same slope. They don't really look like they have the same slope here, but if I manipulate these equations a bit, I would end up seeing that y equals x minus 1 for one of them, and y equals x plus 1 for the other. So, which is why they're intersecting at negative 1. Let's get this over. Negative 1 and positive 1, if you see there. Negative 1 and positive 1. So they have the same slope. And that's why they're parallel, and that's why they have no solution. So when you're taking the test, or you're discussing with your classmates about systems of equations, and you end up with something like negative 1 equals 1, or 0 equals 50, or anything strange like that where the two sides are not the same number, then you're ending up with something that we answer with no solution. And you can write that down. It just doesn't have a point of intersection because they never meet. They are parallel. And so again, we end up with no solution. Let's do one more example together, and that's going to wrap up our notes for today with this final example. Okay, this example is coming out of your textbook again. Same section, 5.4. And we're going to go ahead and do number 4. Number 4 on page 257. And number 4 is 2x minus 2y equals 4, and negative x plus y equals negative 2. Okay, so there's my ordered pair. Again, I am anticipating an answer with an XY ordered pair. And using the substitution method, I'm still kind of stuck here because I can't substitute one variable into another yet. Can you guess which equation I'm going to try and isolate? If you guess the blue one, then you are right. The letters are a lot more simple in the blue one, and so that's the one I'm going to use to isolate the variable y. I could isolate x, but x has a negative on it. I prefer positive, simple variables. So I'm going to isolate y, and to do that, I'm going to add x to both sides. And so I get y equals -2 plus x, or x minus 2. Both of those work. I'm happy with both of them. Okay, so now I've got this isolated equation. Here it is, this stuff. I need to plug it in for y. Okay, y equals that yellow highlighted area. So I'm going to plug that into the red equation. I've got to plug it into red. I can't plug it back into blue itself. That would be weird. Plugging the blue one into the red one. And of course, I'm plugging it in for this variable. I'm working very, very carefully and reading my work slow and steady. I'm plugging in the yellow -2 plus x into the yellow y of the red function. Okay, so 2x minus 2. And instead of writing y, of course, I am multiplying by the expression -2 plus x. And then, of course, I finish off. So let's work carefully through this together. 2x, and watch out for this negative here. A lot of people would miss that negative. I've got -2 times -2, that's a +4. And then I've got -2 times positive x, that's -2x. Okay. And then I continue by combining like terms. I'll combine the -2x and the +2x. And then again, something weird is happening. The x is kind of, in a sense, cancel each other out, right? 2 minus 2, 2x minus 2x, that's 0. And then I've got my +4 still. So it kind of feels like the same thing's happening as the last problem. But look very carefully. When I finish 0 plus 4, that's 4 equals 4. It's similar to the last problem, but not all the way similar, because what's happening here? Here, I've got 4 equals 4. 4 equals 4. And when I've got same, right, the same thing on both sides of my equal sign, that meant infinitely many solutions. If you remember at the beginning of the school year, we were talking about solutions to equations and how many they had. This one, since it's the same on both sides of the equal sign, 4 equals 4, this one has infinitely many solutions. So again, we don't have just one. This was a special circumstance where we had infinitely many. So this was not going to be parallel, because parallel systems don't have an intersection point, and so they have no solution. Any other system has one point of intersection, and so it has an x and y ordered pair as its solution. But this one, where they have infinitely many solutions, what's that going to look like? If you remember from our introduction, that should look like a line on top of a line. So let's see here, and we're going to try and stay color coordinated. So I've got 2x minus 2y equals 4. And let's change this color for a second, because this is supposed to be a red one. So there it is. And for our next one, we've got -x plus y equals -2. And I'm going to make this look a little different. First off, I'm going to change it to blue, and then I'm going to put dots on there instead. So let's look at what this looks like. If you look carefully at our lines here, our blue dotted line is right on top of our red solid line. And so what that means is, basically, these two functions are the same line. And when they're the same line, that's why they have infinitely many solutions. Any ordered pair that I pick on here, this one, this one, this one, any of these that I pick, they would be solutions to the system because it's a point on both lines. In the first example, only one point was on both lines at the same time. In the second example, there was no point on the line at the same time. That's why there was no solution. And on this one, all the points are on both lines at the same time. And so because of that, we've got infinitely many solutions. So as you work through these systems, for the most part, you're going to see an ordered pair as your solution, a point of intersection for two lines. But it is often the case that you will also find situations like this one, number 4, where you have infinitely many solutions. And you know you've got infinitely many solutions when you end up with something like this, the same thing on both sides. And you end up with the situation where we have no solution because you end up with two different things on either side of the equal sign and no variable, of course. So be on the lookout for special systems like this. That takes care of our notes for today. Please make sure that you are putting comments in the discussion board on Schoology so that you can get points for watching this lecture. And make sure you complete your homework in ALEKS. And of course, as always, if there are any questions, please feel free to reach out to me via Schoology or Remind. Okay, it was nice to speak with all of you. I hope to hear from you soon. Bye-bye.